It is my pleasure to participate in this virtual session to honorate Harald Hoyer. As you can see, I picked my background to illustrate that it was supposed to be a conference held in Orlando. The subject of my presentation is the heating of new anode using the waste heat from anode buds, and more specifically to establish the interface thermal contact resistance by comparing measurement of done on some lab tests with some modeling. So I am Marc Dupuis. I prepared this presentation in collaboration with Kristian Etienne Einarsrud and his colleague from SINTEF, Henrik Grudensen, maybe it's pronounced like this. I'm not sure. And this work was financed by NTNU. And if you have any question, you have my email here. So the plan of the presentation is as following. There will be an introduction, presentation of the experimental work, presentation of the mathematical model of the lab experiment, comparison of the lab result and the model result to establish the contact resistance. And then we will present a new proposal for preheating a new anode using the result of the experiment. We'll discuss the subject and then conclude. So for introduction, when we put a new anode, cold new anode in a pot, there's a drastic thermal response from the putting a cold anode into the cell, hot cell, and the cell responds by freezing the bath under the anode. And we can see in this modeling work done and presented Ixoba last year. Work done by Zhao and Hal from SAMI that we can establish a modeling, and of course we in the next slide we can observe that bath is forming, it's freezing under the anode face, and that is preventing the current to flow from in the new anode for some hours. And of course, this requires also energy. Then last year it was established that we can save 0.02 kilowatt hour per kilogram if we preheat anodes using old anode buds. And this is only to considering the latent heat that the heat that we save, that we don't have to provide, the cell don't have to provide. And also we can see on the picture this preheated anode, there's less sludge or freeze form under the new preheated anode compared to the regular cold anode that was put in side by side. And this, of course, since it's beneficial, when in China, for example, they have developed a method that they tested and patented, where they preheat a new anode by putting buds on the first row here underneath, or like here, and then the new anode on top on racks, and then the heat that is dissipating from the buds is preheating the new anodes. This was, of course, tested and patented, but because that was not the most efficient way to transfer the heat from the bud to the new anode, the gain was not enough to justify the extra logistic of doing this kind of operation. so it was abandoned. Okay, so if we go back to our the core work done here, we first want to establish the contact thermal resistance. So we develop an experiment. So in that experiment, we machine blocks of anode, square cube of anode, 10 by 10 by 10 centimeter, and we drill some hole for inserting thermocouple. And from the top anode block that will represent the hot anode butt, we have a rod that will be inserted to be able to manipulate that hot anode block. So this is an extra machining for the hot block. And then the lab the experiment look like this. This is the rod to manipulate the hot block that will be inserted on top of the cold block that is in the bottom of this experiment with all the thermocouple. And then after preheating the block, the top block in a furnace, it is inserted, and then the temperature are recorded. So there will be three setup. The first one, it is a direct contact, so the hot block is placed directly in contact with the cold block. And then the second experiment, the 3 millimeter gap is left in between the two. And third experiment, the hot block is soaked into bath before being put on top of the cold block. So each 3 times we will record the response of temperature. So the temperature response looks like this. We have the 3 thermocouple of the hot block here, and then the 3 thermocouple of the cold block here. And as soon as they are put in contact, there's a very quick response initial, and then a slow diffusion of heat, so that after an hour of the thermal diffusion, the 2 blocks are almost at a uniform temperature, that is the average of the initial 2, about 500 degrees Celsius. Showing that for an hour of thermal diffusion, we can neglect any heat loss of the system. And the initial response depends strongly on the contact resistance between the 2 phases. So to compare with the modeling, we will take this curve, subtract this curve, and the difference between the two will be compared with the model solution of the same gradient. Okay, so this is the setup of the model. So it was decided to build it in 3D, and because we are neglecting all heat loss boundary conditions, and there's essentially no boundary condition in the model, so there's no gradient, horizontal gradient, so we have a very fine vertical gradient, so very fine mesh vertical, and essentially only one element in the horizontal plane. That, of course, if we have to eventually apply some boundary condition, we could remesh. But for this setup, it was the most efficient mesh. So the initial condition is in the model, the top block is cold and the hot block is hot, and is down. And then the two are separated by or contacted by contact element, and then the property of the contact element is the conductivity of the connection, and that is the parameter that we will adjust to match the measurement. So this is, for example, a solution after 10 minutes of thermal diffusion for a value of the contact conductivity at the interface. So this is a solution for not only 10 minutes, but thermal gradient for many different times. From 0, where you have a jump, and then to 1 hour, where you have this still some jump here due to the conductivity. That is not infinite, so that means that there's still a jump of temperature between the two blocks. Okay, so now if we compare with the measurement, they are recorded every at 2 Hertz frequency, so it's a continuous value here. And then the model, we are saving the result every very few timestamps, so those are the points representing the modeling result. Of course, the model is saving with a very much finer time step, but we are not recording all the time steps. So we are comparing the red dots that are the model result with the continuous blue curve that is the experimental result. And for this value of the heat transfer coefficient, we have our conductance, thermal conductance coefficient of 300 watt per meter square degree Kelvin. The model is the gradient is dropping faster. That means that this value is too high compared to the experimental value. So after some trial and error, you get to the right number. In this case, where the two faces are put directly in contact, the right value is 225 watt per meter square Kelvin. So that's the result for experiment 1. Experiment 2, where we have a air gap, the value was much less, turned out to be 80 watt per square Kelvin. For the third one, we are in between. We have direct contact, but with some back film in between. So it's an extra resistance. And for that case, that is most probably the most realistic value, pending some real experiment with an anode butt and a real cold anode. We have established that 100 watt per meter square Kelvin is about the value of the conductance. Then after that, we can use those results for doing some trial of some configuration to preheat. So our proposal in this paper is to put the butt direct bottom face directly in contact with the bottom face of a new anode. Let's assume that we are able to do that easily. So in the modeling is not an issue. So this is the setup. So the temperature of the butt in the model is the temperature obtained from solving that butt or all anode in operating conditions. So we have the boundary condition of an old anode in operation. So the current is flowing through. We have the heat loss from the top and the heat in from the back temperature boundary condition. And so we obtain the steady state operating temperature of that whole anode. And then we take this whole anode solution. We remove the boundary condition that are the voltage boundary condition and the boundary condition from the butt touching the back. And we add a cold new anode underneath. We define the contact element between the butt and the new anode, and that's the initial condition of that model. We can see here in more detail the temperature of the butt, carbon part of the butt, and the carbon part of the new anode. And so from this condition, we simply we are leaving the boundary condition from the air to the rod, but we assume this is inside a box, well insulated, so there's no heat loss on the vertical face of the butt or the new anode. and we leave the system diffuse, and we get those curves. So for this value of the transfer coefficient of 225, that is from experiment 1, we obtain the maximum temperature after about 40 minutes. We reach the maximum temperature of the new anode bottom face, and after that, due to the continuous diffusion of the heat, there's a little drop of that bottom face temperature for the new anode. So depending on the objective of the preheating, we say after 40 minutes, we have obtained the maximum bottom face temperature. So we can put that preheated anode in the cell, or we can wait to exchange even more heat at the expense of decreasing a bit the maximum temperature in the new anode. This is the solution for after 2 hours of preheating. So after 2 hours of preheating, the new anode average temperature of the carbon is 155 degrees Celsius, and the bottom face is 474. And in the paper, we'll presented the solution obtained for the other two conductance. So the 80 and the 100 thermal conductance between the two parts. So now for the discussion. Putting a new using the anode butt to preheat the new anode is in the box, especially designed box, so that we can essentially put the new anode in the butt in, and then we change the configuration so the two bottom face are in contact for a period of time, and then we can reopen this box and then put the preheated new anode in the cell. Is one way to minimize the thermal impact of putting new coal anode in the butt. But this, of course, will require the construction of this kind of box, and then the handling of the butts and the new anodes. So it's an extra logistic that may or may not justify the implementation, as for the Chinese design that was presented initially. It is our belief that preheating the bottom face to 400 degrees Celsius will minimize the thermal impact of, and then we were gonna save a lot more than only the energy to preheat the coal anode. We will be able to most probably reduce the ACD, and there's also some measurement indicating that we can save about 1% current efficiency. We can test the impact of a preheated anode into models like the one developed by Zhao. So in conclusion, first conclusion is that the new configuration is 4 times more effective than the one tested last year, and the paper that initiated the present work. We expect we can get about a saving of 0.2 kilowatt-hour per kilogram mostly by reducing the ACD, improving the current efficiency. Because as we have seen, we have 10% only come from the actual preheating of the carbon. 0.02 kilowatt-hour per kilogram is the actual saving of the energy to preheat the new anode. The rest is saving from operation, so reducing ACD and then improving current efficiency. Despite anything that we can do, we will have to cope with the extra logistic of having this kind of a preheating operation. So what we hope is that we can find a configuration like the one proposed here that may justify the extra logistic. So that's it. Thank you very much for your attention.